All right, chemists, let's get started. So chapter 7, we are halfway done. All right, so Chem 12:10, we cover chapters 1 through 12. So 7 kind of marks our halfway point. So you've made it halfway now. So I'll mention here, 7's a pretty short chapter. I do hope to finish it this week. Memorize some of those periodic trends and connect them to the N level and the concept of Z effective that we'll learn about here today. All right, so chapter 7, we're looking at periodic trends. All right, so we're diving deep into the periodic table. If you remember from chapter 2, when we named things, I told you to just memorize, lithium forms +1 cations, magnesium forms 2+ cations, oxygen 2- anions, fluoride -1 anions. Those things we just kind of memorized and maybe took for granted. So in this chapter, we actually put energy terms to the idea of forming cations or forming anions to give reasons to, why we only find sodium plus. We never find sodium 2+ in nature. We only find the +1 version. So this chapter explains those answers or has those answers in terms of energy terms. Hopefully that makes more sense here. The biggest concept in this chapter, and the concept that you probably never experienced before in any of your high school chemistry, is the concept of effective nuclear charge, or oftentimes labeled Z effective or ZEFF, Z effective. This is a new concept, and this concept that we'll talk about today, I have some good analogies to think about it, is what explains a lot of our trends. It's not just, like memorizing the trends. These trends are based upon factual things that we can measure, like effective nuclear charge, the attraction that an electron feels to the nucleus. So we'll talk about that today. Good thing about, chapter 7, we will, if we think about looking forward to midterm 3, I forgot. You guys got your midterm 2 scores, right? Yes? Like shortly after you left, right? Yeah, I had to email them and they opened it. Our class, the average was a 65% in the class, all right? And the average across all sections of Chem 12:10 was a 67%. So just to put that into perspective, all right? So I think that's really good, all right? That we're really close to the average. That's great. All right, so just, this was us, this was them, or everyone. So including my other class as well. All right, so the good thing about, so let's look ahead to midterm 3. All right, so do think about the strategies you use for midterms 1 and 2. This is kind of like your second to last chance to kind of turn things around if you're thinking about a new learning strategy that you want to approach this class with. I will let you know that the next midterm, covers 7, 8, and 9, those chapters. There is very little calculations. All right, so we can put our calculators away for a while. I wouldn't be too happy about that. All right, so just, there's comfort in numbers. Okay, there's comfort when it's conceptual, like you need to know it. You need to know it really well. You can't just smash numbers together. So this next part, like whoever has recitation this week, there's a new packet. I posted the new packet. The first page is always like what I think the supplemental packet will be. When you look at that page, you'll see it's very empty. It has the periodic table and it has a couple diagrams. It has no equations, it has no constants, because we're not going to use those in the next couple chapters. So it's all very conceptual. So we might want to approach these next chapters a little bit differently. I would suggest after every one of these lectures, just take a couple minutes and review what we went over in class. Maybe do a couple practice problems, because it's not like, numbers that you can crunch and practice. You need to be assessing yourself, using these concepts, coming up with the trends, and using that outside of class. And I think that will help us improve our midterm score for the next midterm, which is mostly conceptual. Honestly, if you forgot your calculator to midterm 3, it wouldn't be a big deal. Honestly, that's how it is. All right, so chapter 7, we're talking about periodic trends. So let's forget for a minute that we know what the periodic table looks like. Right? That's our modern day periodic table. We want to think about, okay, how did scientists first come up with the periodic table? So oftentimes when you know, Wikipedia periodic table, what you'll often see is the name Mendeleev, Dmitry Mendeleev, come up. In high school, you might have learned that he was credited for, discovery or organizing the periodic table. Not that he discovered the elements, he literally just organized it. So he put the puzzle pieces together, all right, to figure out, what our modern day periodic table looks like. Because it's this funny shape, if we think about it. It's the reason that the periodic table is this funny shape is that we have the S block, the D block, the P block, where all of those valence electrons are nicely ordered up. And so Mendeleev was the one who was able to see this periodic, periodic trend kind of pop up over and over and over, and was able to put together the modern day periodic table and its shape. We have our S block, our D block, our P block here. So if you look a little bit closer into history, you'll see that actually two scientists at the same time, all right, in like the late 1800s, came up with the idea that the organization of the periodic table at the same time. But no one remembers Meyer. No one remembers him. Everyone remembers Mendeleev. And there's a reason Mendeleev was a genius. At the time, all right, in the 1860s, did they know what electrons were yet? Did they know what protons were yet? No. So in the late 1800s, Dalton's billiard ball model was still like supreme. Like that's what they thought atoms were. They thought that they were these indivisible balls. So we had no idea about the electronic structure, all right? So do recognize that coming into this story. Don't use our biases that we already know what this looks like. The reason that, Mendeleev is remembered and not Meyer, again, he didn't know what protons and electrons were. He didn't use that idea to put together the periodic table. He saw what like these periodically the same properties would pop up over and over. And he decided to put in columns those similar properties in the same column. And that kind of sounds like what we've been utilizing this whole term. Like we know all group 1A elements form +1 cations. All 2A form 2+ cations. That's what Mendeleev put forward here. But the reason that we remember him and not Meyer is because, hey, this is the 1800s. Not all the elements were known yet. Right, so what we see here is like some of these yellow things that we see here. These elements were not discovered yet. All right, they were not isolated yet. They didn't have properties for them. So the reason we remember Mendeleev is that he was smart enough to realize, hey, I have a missing piece. I have an element that should come next with these properties, but nothing like that exists. So instead of just trying to smash the puzzle pieces together to make it fit, he left a blank. He knew that he was missing pieces to his puzzle. And that's why we remember him. And so with those missing puzzle pieces, he knew and predicted what properties they should have. He even suggested where to find it, which is kind of the amazing thing, that he didn't just think, oh, these are all the elements, these are all of them, and just try to fit it all together to make it look nice. No, he left blanks knowing that these things didn't exist yet. It just will take time to find them. And that's why we remember him. Okay, and so that's what you see here. He called this blank right here, so he saw like, oh, there's a missing piece. It should have these properties. He called it silicon, meaning that it's below silicon. It should have similar properties. And later, a couple probably decades later, we did isolate it and we called it germanium at that point. And that's why I remember Mendeleev. All right, so this is, I know it looks very different than our modern periodic table, but this is his periodic table. So here's a question. What information did Mendeleev use to group the elements in his periodic table? A, B, C, or D? What do we think? What do we think? This seems like an easy question, but it's tricky. Okay, so does anyone want to be brave? Yeah. B, do we agree with B? Yes, he used B. Boiling point in order to organize his periodic table. Remember, this was like the, what did it say, 1890s or something, like late 1800s. They didn't know what electrons were. They didn't know what protons were. Yes, we know that they're ordered in terms of atomic number, like we know that, but he didn't. And so he used properties that could be measurable at the time, things like archaic things like boiling point, or like conductivity, things like that, that he could actually measure at that time. They didn't know what electrons were. So that's a tricky question, because if you let your bias like overtake you, you'll get it wrong. All right, so we get that, use boiling point. Okay, all right, so let's go now talk about the modern day periodic table. We know it's shaped this way because we organize things in terms of properties. We have our S block, our D block, our P block. We use those terms to help us come up with electron configurations. And again, this organization scheme, it's all put there this way because we want to put in the same column similar electron configurations. It's all made this way because of the arrangement of their electrons, specifically valence electrons. And we'll learn here soon that valence electrons, these are the ones that are involved in chemical reactions because they are furthest. They're on the ends, the outside of our atoms here, right? So rows we call, horizontal rows we call period numbers. That is related to our quantum number n that we talked about in chapter 6. So as we go further down the periodic table, larger ends, typically our atoms get larger because we have multiple energy levels outside going further away from the nucleus. That's what the horizontal rows mean. The vertical columns, we've been referring to these as groups in this class. All right, the group number typically represents the number of valence electrons in that group. That was our quick and dirty way that we calculated, number of valence electrons. That sodium, we know it's group 1A, it has 1 valence electron, but if you write out the full electron configuration, you'll also prove to yourself it has 1 valence electron. But the quick and dirty way is just, through group number. All right, and again, so all of these things together, we organize it this way because, chemistry is a lot about predicting reactivity, predicting properties. So if we organize the elements this way, it's easier to read. All right, so Mendeleev put together the periodic table in terms of just similar properties in the same group. Okay, so how did we actually get the modern day periodic table where we know that the order goes in increasing atomic number? Right, so we're getting closer to the modern day periodic table where we know it's organized by protons. How did we get to that point? So that whole idea of atomic numbers was credited by Henry Moseley. All right, so you can see from the years here, he lived a really short life. He was drafted in the war. So first he was credited with discovering the atomic number, all right, and ordering the periodic table, but then he was drafted in the war. But he had a lot of impact on chemistry. So his contributions here actually fixed some of the small mistakes Mendeleev had, all right? So Mendeleev, he did, swap elements, okay? The data he was using was very archaic, but Moseley's experiment here basically put in order all of the elements. And these are his observations, and I'm gonna try to explain it the best I can. He took each element, all right, that was known at the time, and he bombarded them with high energy, all right? So he excited these elements. And what he saw is when he excited the electrons really high up on the element, the electron would fall. When an electron falls, what happens? It releases energy in the form of a photon. Okay, very good. All right, so he is exciting these elements and he's observing photons. Specifically, he observes X-rays, and he sees that all elements emit X-rays when he excites them. The difference is here is that every element emits a different frequency of an X-ray. All right, so all the elements emit different frequencies of X-rays. So then he noted that if he ordered the frequency of the X-rays on a graph, that's what we see here, all right? If he ordered them, he saw that they all fit on a line, all right? He did this for a lot of different elements. He saw that the frequency would increase. He put all of them in a line. He saw that it matched the order that Mendeleev came up with very slightly. That it matched most of the time, but this is what he saw. So what he did was labeled the x-axis a number that he just called atomic number. All right, he just called it atomic number, saying, okay, these elements are lighter, they have lower atomic numbers, these ones are heavier, they emit higher frequencies, they have a higher atomic number. Later, we will learn that atomic number means what? Number of what? Protons. We will learn that here soon. And so that's what he deduced. He deduced that atomic number, the higher the atomic number, the more protons in the nucleus. All right, so higher atomic number means higher frequency X-ray emitted. He deduced was a larger number of protons. I'll try to explain how he got to that conclusion. All right, so here's the conclusions. He saw high energy X-rays with increasing atomic number. So again, atomic number means number of protons. What this means is that when there's more protons in the nucleus, the N equals 1 energy level, so remember from chapter 6, is lower, it's more negative. And so that means when an electron falls, it's gonna fall further. And that's why a higher energy photon is emitted. This is the observation, but I think this slide describes it much better. All right, so let's think about the X-rays emitted here. So I have two examples. I have a hydrogen atom and a helium atom. So which one has the higher atomic number, hydrogen or helium? Helium, it has more protons, right? It has 2 protons. So let's think about an electron on hydrogen and helium and see if we can't recreate Moseley's experiment with concepts we already know, all right? So do remember, when light is emitted, an electron falls, right? An electron falls. So we want to think about, okay, how does that fall relate to the energy of the photon that's emitted? So let's think about this. Imagine we have an electron, orbiting around hydrogen versus an electron orbiting around helium. So you see the difference is the charge of the nucleus. That on hydrogen it's +1, on helium is +2. So pretend that you are an electron on hydrogen and you're looking into the nucleus. What attraction does that electron feel? What kind of charge? If the electron on hydrogen looks into the nucleus, what kind of charge does it see? +1 versus on an electron on helium, if it looks in, it sees a charge, an attraction of +2. So this first question here, which electron is more attracted to the nucleus? The electron on hydrogen or helium? Helium, yes, because it's around a +2 nucleus. Okay, so remember from, what is this, chapter 5 or 1, I don't know. When you have a high attractions in terms of potential energy, where is that on our graph? Is that really positive? Really negative? When you have high attractions. It's a very negative number. Yes, it's a very negative number. So that's why I've drawn these 2 energy level diagrams. See these? These 2 energy level diagrams? See how on the helium atom, N equals 1 is lower. It's more negative because more attraction means more negative potential energy. Is that the next question? Which electron possesses a more negative potential energy, hydrogen or helium? So again, it's helium. It has a more negative N equals 1. See, we know, we don't know all that. We can put that together with things we already know, all right? Okay, now imagine, here are our ladders, okay, rungs on our ladder. If we have an electron falling from, let's say, infinity, which one falls further? The electron going to a hydrogen N equals 1 or to a helium N equals 1? Helium, yes, because the N equals 1 is lower for helium. So which one falls the most? Helium. Okay. So we see how we got that. There's a larger fall for the electron on helium because there's more protons in the nucleus. So finally, let's relate this to X-rays, what Moseley actually observed. So a large fall means what in terms of the emitted photon? Large or small energy? Large, yeah, large fall, large energy, so large. Okay, so then how does the energy of the photon relate to its frequency? Up, yeah, both go up in that case. So as frequency of emitted photon increases, there we go. So that's how all of this comes together with Moseley's experiment. More protons, all right, in your nucleus, you'll have a lower n equals 1, all right? So you have a larger fall, and so that means the energy and the frequency of your photon increases of whatever is emitted. And so that's how all of that comes together. And so that's my best interpretation and explanation of this. If you read the book, there's just one short paragraph about Henry Moseley. But I think this idea, relates to chapter 6 wonderfully, and how the idea of attractions, electron attractions to the nucleus kind of is like a preview to what we're about to talk about now. All right, good. So the whole idea, more protons, higher energy, photon emitted. He put them in order. And actually, when he put them in order, he fixed some of Mendeleev's elements. Because if you think about it, your intuition when you order things like this is to put things in increasing weight, like it should go in order of weight, right? Like it should increase in weight for every element. But if you look really closely at the periodic table, there's a couple instances where the element before it is lighter. So I think an example is cobalt and nickel. Cobalt's 27, nickel is 28. Cobalt is actually heavier in terms of its molar mass than nickel. And so Moseley's experiment was able to fix that, while Mendeleev probably flipped them. Because our intuition, our human minds we just want to put everything in order in terms of like weight or number. But it was Moseley's experiment that deduced, hey, we should order this in terms of protons, not properties like mass. Good? All right. So this whole idea of us pretending we're an electron looking into the nucleus, this is coming up again, and that's the most important concept in this chapter, and that is Z effective nuclear charge. There's only one equation in this chapter, and it's this one right here. It's this one right here, and that's why you're not given it at exams, because it's just that, all right? Where Z effective, how I like to describe it is what attraction an electron feels in terms of where it is. Because the idea is if your classmate right here is an electron, would they feel more attracted? And I'm a nucleus. Let's say I'm like +5, okay? Would she feel more attraction if I'm right here really close to her, or if I'm really far away over here? Yeah, when I'm close, the electrons feel more attraction, versus if I'm far away, there's less attraction. And so that's the idea of effective nuclear charge, is the attraction electrons feel in terms of where it is relative to the nucleus. And so we calculate it by taking inventory of the charge of the nucleus. So that's what Z is. That's related to the identity of the element minus the shielding. So shielding is any electrons that are standing between the electron of interest and the nucleus, right? So this is an example I like to give, all right? So let's say I'm a +5. I'm a +5 nucleus. Okay, you're an electron. If I stand right here, what kind of attraction, if you're looking into the nucleus, what attraction do you feel? Yes, give me a number. Or sorry, if you look in, what type of positive charge do you see? If I'm +5. Just say +5. Yeah, you look at me and you see a +5. You see what I'm saying? Okay, what about you? What do you see? Yes, okay. What about you right there? Remember, you're an electron. Your classmate's an electron, but I'm standing right here in front of you. So there's an electron in the way. So do you feel the whole +5? No, what do you feel? You feel less, right? So if there's an electron in the way, count up all the charges in front of you. I'm a +5, he's a -1, so you feel a +4, right? Okay, and then what about you up there? How many electrons are between you and me, a +5? You would feel +3 because there's 2 electrons shielding you. Exactly, all right? So that's what shielding is, that we are, we're pretending to be electrons, but there's also electrons between the nucleus and you, so we have to take into account of that. So that's what we do here. So Z effective, it's the effective nuclear charge that a specific electron feels. We need to take into account the nucleus and the shielding that's present. So I like to use analogies here, but here's the strategy real quick to get Z effective. So using this equation, determine what the element is, so what Z is for that specific element. So if we're talking about sodium, then it's plus 11. Determine the screening constant, right? This is, you count the number of electrons between you, the electron of interest, and the nucleus. And then finally, you just do the math, all right? Did I miss some things here? No, I didn't, all right. And so I want to do an example before I do an analogy. So let's actually do the example, go through these steps. So let's calculate the effective nuclear charge of an electron on sodium. So a good thing that will help us, all right, is, so let's look at these examples here, is if we write the electron configuration of sodium. So that's the full electron configuration. It's better if you do full. So for sodium, what is Z? What's the charge of the nucleus? Plus 11. I like to use like, pluses and negatives so we can clearly see like what's attraction, what's repulsion. So these are the electrons that are around it when you write out the electron configuration, right? So I oftentimes like to write, okay, here's my plus 11 nucleus. Here are all the electrons looking in, like sitting in a line looking into the nucleus, all right? So just like, me standing right here and you thinking, okay, what charge do you see when taking into account of electrons between you, we're kind of doing the same thing. So if we are a valence electron on sodium, so that means we're this electron, we're a 3s electron, and we are looking in to the nucleus. We already know what the charge of the nucleus is, the full charge, so like me standing right here. Now we just need to figure out how many electrons are standing between me and the nucleus. So how many electrons total are between the 3s electron and the nucleus? We can just count them, right? It's all of these electrons. Whoops, too many. All of those lower n value electrons are closer to the nucleus. They're blocking the full charge. So in this case, what is the shielding constant? Be 10. Yeah, there's 10 electrons there, all right? So Z effective would be 11 minus 10 equals plus 1. So that means that valence electron, when it looks into the nucleus, it actually only feels a plus 1 charge. That's how attracted it is to the nucleus. The idea is like if I'm plus 11, and someone's sitting all the way back there, they're not going to feel, if they look towards me, they're not going to feel the full plus 11 because there's a bunch of electrons in the way of them feeling the full radiance. Okay, so let's do Z effective for another electron, this time an n equals 2 electron. N equals 2. It's the same idea for sodium. So we still are working with a plus 11 Z because it's sodium, but now we're not this 3s electron. No, we are now a n equals 2 electron. So we are in n equals 2. So we are these s and 2s and 2p electrons, both of them. And so then we look in to our nucleus, which is plus 11. So now the question is, what is our shielding for these 2s or these n equals 2 electrons? What's our shielding? How many electrons are standing between n equals 2 and the nucleus? This time, yeah, only 2. It's only those n equals 1 electrons. We only count lower ends. So in this case, shielding is 2. So our effective nuclear charge for these n equals 2 electrons is 9, plus 9. So we see that those n equals 2 electrons, when they look into the nucleus, they're actually experiencing a higher attraction. All right, yeah, I think I answered that question. Which electron's more attracted to the nucleus? So in this case, it's n equals 2, because valence is n equals 3. All right, and so the idea here is for this last one, when we counted effective nuclear charge, we don't count the 2s or the 2p electrons in the shielding constant when we calculate shielding, because they're in the same, I like to think they're in the same row. They're not affecting, it's like the idea of like you're looking at me, you feel the full charge, but is the electron sitting next to you, are they affecting the full charge that you see? No. No, so electrons in the 2s are not shielding one another. It's only inner electrons that shield. Okay, so now I will talk about my analogy. Okay, because if you read the book, they show pictures like this, all right? Okay, yes, we're a valence electron. These inner ones shield the full charge of that nucleus. Or they use this weird eyeball with a light bulb, a frosted light bulb, to show the frosted glass is shielding the full charge of the light bulb. I like to use this analogy with Taylor Swift in her short hair days. I always had this in my slides. I know she just came out with a new album on Friday. I can't actually get into it. I liked her old stuff. But I think this is a good analogy because this kind of looks like an atom, right? Where Taylor is the nucleus, and all these people around her are the electrons. So let's think about it. Someone give me a positive charge for Taylor Swift. 10? Okay, so she is plus 10. That's the nucleus. All right, plus 10. So think about where the people are sitting. The people who are right around the edge of the stage, the people who are just touching her shoes, what kind of and remember, all of these are electrons. What kind of charge, attraction do they feel towards Taylor Swift? So if you're this electron right here, if you're that person looking in, you're touching Taylor's shoes, what type of charge do you see on Taylor? The full plus 10, right? Because is that guy being shielded at all? No, he paid a lot of money to be in n equals 1. Okay, then things change as we start backing it up, right? Like if you're this person and you look in, are you going to feel the full plus 10 of Taylor? No, there's a bunch of people shielding you, all right? So you have to take into account of that. So it's the charge that person feels will be less than 10. I don't know what it is. Let's say it's 9 or something, something like that. They're not going to feel the full plus 10. But then the question is, so if you're this guy, okay, you're this guy looking in, okay? It's only the people directly in front of him that are affecting Taylor's full radiance. Does the person next to him really affect his concert going experience? No. And so that's the whole idea of, when you're focusing on an n equals 2 electron, shielding, it doesn't count. The electrons inside, in the same shell or in the same n value don't affect effective nuclear charge. Does that make sense? Yes. Okay. And then lastly, let's talk about someone like over here, all right, way in the back. Do they feel more or less attracted to Taylor than the green guy up front? More or less attraction. The person all the way back here. Much less attraction. So do you think their focus will be on Taylor? Will they be focused on her? No, if a beer cart comes by, they might be distracted. And so what we'll learn here, when electrons have low effective nuclear charges, when they're not super attracted to the nucleus, they are easily picked off. They have very low ionization energies. It requires very little energy to pick them off because they're not attracted to the nucleus. So that guy sitting in the way back, they're going to be distracted by their phone or whatever, but the people up in front, they're going to be immersed in Taylor's radiance, probably. I've never seen her. So that's my analogy. All the people standing in front of you is part of shielding. The people next to you are not. Okay, and so the method that I described here, it's called the inner core method, where we just count electrons in lower n values to calculate shielding. It works very well. There are more sophisticated methods to do it, but we see that even the inner core method works really well. I'll just mention again, one more time. So this guy, all right, this guy, when we look in, we said that the people in front of him affects Z effective, that these guys are shielding him. What about the electrons behind him? Does that affect shielding? No, it does not. All right, no, it does not. So in this example where we calculated effective nuclear charge of a 2s electron, All right, we didn't have to do anything with those 3s electrons because they're sitting behind. They're sitting behind them, all right? And so kind of putting it all together, given these numbers, a Z effective of +1 or a Z effective of +9, with that in mind, which electron do you think is easier to take off? An N equals 3 electron on sodium or an N equals 2 electron on sodium, based upon the Z effective we just said? 3, yeah, because that electron only has a +1 attraction, so it's going to be easy to pop off, versus a +9, there's going to be really high attraction there. It's going to take a lot of energy to rip off. Also, N equals 2 is an inner core, so that kind of makes sense. But it should make sense in terms of energy that we're talking about here. All right, so that's Z effective. So let's go through this. All right, let's look at the trends. Okay, so here are a bunch of elements: lithium, boron, oxygen, neon. What is Z? What's the Z component of Z effective? What does that mean? Number of protons. So how many protons does lithium have? 3. What about boron? 5. Oxygen? 8. Neon? 10. Okay, very good. Now the hard part is to calculate shielding. We want the shielding of the valence electrons. We're focusing on valence electrons here. So again, pretend you're a valence electron on lithium and you're looking into the nucleus. How many electrons are standing in front of you? 2. Okay, very good. What about boron? In this case, you're still an N equals 2 electron, and you're looking into the nucleus. What is your shielding? Also 2, yes, also 2. What about oxygen? Also 2. Do we see kind of a pattern here? All right, and then finally neon. Where are our valence electrons? What N value are they in? We're still in N equals 2, yes. All right, and then we look in, how many electrons are shielding? Still 2, okay, very good. So we have our Z, we have our S. Now we can calculate our Z effective, which remember is just Z minus S. So let's put that together. So Z effective for lithium is 1. Boron is 3. Oxygen is 6. Neon is 8. Okay. Are there any clever people out here who see a trend with these numbers? 1, 3, 6, and 8. And then you look at the periodic table. Do you see? Yeah. So what's the quick and dirty way to calculate effective nuclear charge of valence electrons on these elements? It's just their group number. Their group number. So you see lithium is in group 1A. So on its valence electron has a effective nuclear charge of +1. The next one, boron, group 3A. That's it? Yeah, that's it. But this is just for valence electrons. So boron +3, and so group 3, same thing with oxygen, group 6, and then neon is group 8. So the idea here is all of these are positive values. So when these highlighted electrons are looking into the nucleus, when this electron looks into a nucleus, it feels a +1 charge. These N equals 2 electrons on boron look in and they see a +3 charge. They don't see the full +5. Oxygen, these N equals 2 electrons see a +6, and then the N equals 2 electrons on neon see a +8. And so the quick and dirty way is it's just the group number. But this is just for valence electrons, all right? And it's just for your S and P block elements. It works for that. So that's across a table going left to right. So that's nice, right? Versus, let's go down the periodic table, okay? Magnesium, calcium, and strontium. What should the effective nuclear charge be for all of those, based upon what we just said? 2. They should all be 2. Do you see how I get that? Because magnesium, calcium, and strontium, they're all 2A elements, right? But let's calculate it anyway. Magnesium has 12 protons, calcium 20, strontium 38. And so the shielding for all of them will just be the noble gas before them. So for magnesium, it's 12 minus 10, 10 electrons coming from neon. For calcium, it's minus 18 because that's the inner core of calcium. And then for strontium, it's minus 36. So we see how we get that positive 2 for all of them. But the thing is yes, when we do the quick and dirty way, it's a 2A. 2A elements are plus 2. But what we actually observe is that Z effective slightly increases as we go down a group. So it really should increase. Should increase. And the reasoning is when we calculate Z effective is Z minus S, so charge of your nucleus minus shielding. When atoms get really, really big, okay, and you think about the effects of shielding, we're saying that every inner core electron shields perfectly, all right? But when atoms get really, really big, those inner core electrons shield less effectively. So as our atoms get really big, S is actually smaller than anticipated. So that means Z effective is actually larger than anticipated. So the idea here, and I like to do an analogy. If I go back to Taylor Swift, Swifties. All right. If you are in the nosebleed seat, say you're this person, and you look in with a Z effect, like you have some type of attraction towards the stage, you're in the nosebleed seats. Is it gonna make a difference if you're sitting there where the red dot is, or if you're sitting here where the pink dot is? Is it gonna make a big difference? No, because you're already so far away. So Z effective doesn't really change that much. Shielding isn't is not changing as much when you're already so far away. Versus if you had the choice between sitting here, okay, where this green dot is, or here where this red dot is, where do you want to sit? You want to sit at the green dot, yeah. So when you're close, bigger dramatic changes happen. When you're further away, shielding is not as important, but up front, it really is important. Okay, so that's my analogy there. Okay, so there we go. That's effective nuclear charge. Keep this in your back pocket. Try it out. It's going to basically explain everything. Because think about it. Z effective, it's the attraction an electron has to the nucleus. So if an electron experiences a high Z effective, it's highly attracted to the nucleus. So is it going to be easy or hard to remove it? Hard. If it's highly attracted, then it's going to be hard to rip them apart. Versus if it only feels a +1 attraction to the nucleus, it's going to be real easy to pop that off. Right? So that's going to come back again. All right. So in the next part, we're going to look at sizes of atoms. Thankfully, we'll look at the trends that I mentioned before to get there. But let's first think about how do we get the size of an atom. The size of an atom. Who took the EMS lab? Everyone? Half of you? Do you take it this week or no? Last week, on Thursday. Tuesday. Okay, so then everyone did it. All right. Right? Yes, okay. People just don't want to raise their hands. It's fine. So the idea is that EMS lab where you looked at the electronic structure of an atom, the whole idea is we want to kind of locate the probability of finding an electron. So that probability, those clouds define the size of our electron. You saw that n equals, 6 electrons, they're way far out from the nucleus, versus n equals 2 electrons, they're real close. All right, so that whole idea of where to find electrons dictates the size. Okay, so when we look at size of atoms, we're really just looking at the valence electrons. Where are the furthest electrons away? So mathematically, how we figure out the size of an atom is we have to solve the Schrodinger equation, because remember, the electrons define where the atom begins and ends. We need to figure out where the electron is, so we need to solve the Schrodinger equation, right? Right. So here's a graph of the radial distribution function, like from chapter 6, of a bunch of particles here. These are all special because all of these particles have 1 electron on them. Hydrogen, a helium plus cation, a lithium 2 plus cation, they all have 1 electron. So we're trying to locate where is that electron, and that will tell us the size. So based upon this graph, when we solve the Schrodinger equation, which graph shows the smallest atom? Smallest? So remember what this is saying. This is radius. So if we think about a sphere, and the radius of that sphere, okay? So this is the probability of finding the electron. So if you think about hydrogen, could you find an electron at, whatever unit this is, 4 angstroms? Is this graph saying you can find some? Yes, there is, because there's a little bit positive graph, but will you find an electron on a lithium 2+ at that same length? No. So try to answer the question again. Which particle is the smallest according to this graph? Lithium 2+. That graph is indicating, hey, most of the electron density is within 1 angstrom, or whatever unit this is. I have no units. 1 angstrom of the nucleus. So lithium 2+ is the smallest. Okay, so the graph says lithium 2+. So you see that? You see that? So relate this to the idea of radial nodes from chapter 6. The further the graph goes out, the larger the atom, okay? So thankfully, we don't have to solve the Schrodinger equation to answer questions like this. We actually can just use the effective and get the same answer. So in the back of your mind, remember the smallest ion or particle according to the graph is lithium 2+. So let's see if we can't get the same thing. So it's kind of like the Moseley thing again. We have different nuclei, different number of protons, and we have an electron orbiting it. So we want to pretend to be an electron, look into the nucleus and think, okay, what kind of attraction does that electron feel? So for hydrogen, if we are that one electron orbiting hydrogen and we look in, what effective nuclear charge does that electron feel? What charge does it see? +1, because is there any shielding here? No, there's no shielding. All of these electrons are just like right up against that nucleus. What about the electron on helium? If it looks into the nucleus, what is its Z effective? +2. And then what about that lithium electron? What does it feel? +3. Okay. So I answered that. What's the attraction each electron feels? So if you were an electron, remember, as an electron, what's your charge? You have -1, you're a negative charge. If you are just a dumb electron floating around, that's a negative charge. Like a moth, pretend you're a moth. That's negative charged. Where are you going to be most attracted? To a +1 or a +3? +3. You're going to, if you're just a moth, right? A negative moth floating around, you're going to be more attracted to the +3. So with that in mind, what particle is going to be the smallest? The lithium one, because that electron feels the most attraction, so it's going to get closer to the +3 nucleus versus the +1 on hydrogen. It's going to be a little bit further away because it's not as attracted to the nucleus. So see how we could get the same conclusion here, that the smallest particle is lithium. Okay, the lithium 2+, and we didn't even have to solve the Schrodinger equation. Thank God. All right, and then which is the largest here? The hydrogen, because it's the least attracted to the nucleus. Okay, so do really spend time understanding effective nuclear charge. Really, it's attraction of that electron to the nucleus. So it helps us figure out, energy to pop those electrons off. It also tells us a little bit about size here, like we just did in this example. Excuse me. But we don't have to solve the Schrodinger equation. Really, in the next part of this chapter where we just look at the trends, it all boils down to 3 criteria. All right, we'll constantly refer to talk about these different trends based upon the periodic table. So one of the first criteria is Z effective that we already talked about. So do really understand Z effective, and remember the quick and dirty way to figure out Z effective of valence electrons is what? Group number, yes. And then next is we inspect the N value, the energy level of that valence electron. That can also help us determine different trends as well. So keep those 2 in mind, all right? Because, I have the 3 criteria here. So the first 2 I already mentioned. We want to know the N value of the electron, all right? The N quantum number of the valence electron that we're interested in. We want to know the effective nuclear charge. Okay, we want to know how attracted that electron is to the nucleus. That helps us come up with trends. And the last one here, which I didn't mention yet, is extra attractions or repulsions that are made from charged ions. All right, so I'll mention that in a couple slides here, from charged ions. There's extra, sometimes repulsions or attractions when things are charged. All right, okay, so let's talk about size. So let's do the easy one first. When we go down a group, when we go up from lithium, sodium, potassium, rubidium, what quantum number, what criteria changes? N changes. Does Z effective change? No, it doesn't. They're all +1. So it changes a little bit, but the important thing here is that N changes, okay? So when N changes, think about the Bohr model, all right? When N increased, the electron, was it closer or further away from the nucleus? Further away. So same idea here. And when we go down a group, N increases, so the size increases. That one's easy. Heavier things, bigger. Where things are weird is left to right. Because left to right, the size actually decreases. So if we go from sodium to argon, sodium is a lot bigger than argon, which is weird because sodium is almost half the weight of argon. Argon is almost twice as heavy, right? Right? If you look at its molar mass, it's like 40 versus sodium's like 22 grams per mole. But sodium is a lot smaller. Isn't that kind of counterintuitive? Like things get heavier, they should get bigger, but it doesn't. But the reason is this isn't arbitrary. It has to do with effective nuclear charge, all right? So effective nuclear charge going left to right. And the reason, if we think about this, effective nuclear charge, when we go from sodium to argon, how does it change? +1, +2, +3, it increases, right? So the valence electrons, do they get more or less attracted to the nucleus as you go left to right across the periodic table? Z effective increases, right? So there's more attraction. So as we go left to right across the periodic table, those valence electrons actually get more attracted to the nucleus. Yeah? So that would imply if more attraction means smaller atom. And that's why argon is a lot smaller than sodium. And so that's what I mean there. Okay, so there we go. So here's a kind of like proof of showing you that like here are the sizes. Here's sodium, all right? And then chlorine over here is, a lot smaller than sodium. And again, because of Z effective. These are +1 Z effectives, while over here we have +7. So these guys over here, if you are comparing things in the same row, there's a much higher attraction of those valence electrons to the nucleus, and that's why they're smaller. So again, this left to right idea is not intuitive. We want to think, hey, atomic number increases, size increases, but that doesn't happen here. It doesn't. Size actually decreases, and it's because of effective nuclear charge, increasing left to right. So let's see if we can't do this. Let's compare the Z effective of carbon and fluorine. So what's the Z effective of carbon? +4? You did it the quick and dirty way? Yes. Okay, what about fluorine? +7. Yes. So these numbers, these attractions are what the valence electron feels when they look into the nucleus. So in which atom is smaller? Carbon or fluorine? Carbon? Fluorine, yes, fluorine, its valence electrons are more attracted. If you're more attracted to something, are you going to stand far from it or close to it? Close to it, yes. So you're going to be smaller with a +7. Okay, all right. Okay, so transition metals, as always, harder to predict. Everyone's favorite. But let's kind of review some of these topics. In general, when you're looking at sizes, you want to inspect N first. If elements are in the same N, then you look at Z effective. So if we kind of look at this chart with all of these trends here, let's look at the big jump between argon to potassium. See how there's a huge jump in size? Look at where they are on the periodic table as we go from argon to potassium. What factor explains that huge size increase? What's changing? Yeah, N is changing. So in argon, we're in N equals 3. In potassium, we're in N equals 4. So that's why potassium is so much bigger. So this is N equals 3. N equals 4. And so that's why potassium's so much bigger, because we literally had to like rent out a new floor on the hotel of potassium, like a whole new floor, to put that one electron. So that's why it's bigger. All right, okay, so that's why there's that huge jump. N is changing. What about this gradual decrease from sodium to argon? See that size decrease, sodium to argon? So look at where that is on the periodic table. Okay, so sodium to argon is all N equals 3. So what explains the gradual decrease there? Z effective. And again, because all of these elements are in N equals 3, it's all the same. So once we look at N values, okay, if you can explain the difference with different N values, great, then you're done. But if you have two elements in the same N, then you have to look at Z effective. That's like the next like line of attack to figure out a difference. And then you look at Z effective there. All right, so that's the easier one, okay, the main group elements. Note what I have circled here are these weird, see how the transition metals that are in green here don't fit the trend, where we have like a sharp increase, a gradual decrease, sharp increase, gradual increase. Once we get to the D block elements, like always, they're always the weird ones, but it's okay. I like transition metals because they're the pretty colors. So you just got to deal with it. Yeah. So our D block metal, see how it goes down initially. So here's like scandium, all right? That if you go to scandium to titanium, the size decreases until you get like halfway through, and then it starts going up again. And then we get to the P block metals, and then it follows the trend like normal. So what is this down then up thing? Let's think about it. See how the beginning of the D block follows the trend? All right, that the size decreases. So this gradual decrease at the beginning of the D block is explained by increased effective nuclear charge. So the same reason as before. Same reason as before as we go left to right across the periodic table. The exception is the end of the D block. So like D7, 8, 9, 10, the end ones, the size actually increases a little bit at the very tail end. And the reasoning is you're shoving 10 electrons in the same space. Electrons are what charge? Negative. So if you try to shove 10 negatively charged electrons in the same space, what kind of force are you creating there when you put a bunch of them in like one small space? Repulsion, yes. So if you have a ton of D electrons, so like 8, 9, 10, whatever, you start to create more repulsion. So that's why the size increases a little bit, because you're completely filling the D shell, and then you get to the P block and it Z effective takes over again. So that's the small blip that you see goes up is explained by just additional electron repulsion as you completely fill that D block. So that's the main thing there. All right, okay. So, all right. Okay, so remember, size can usually, for neutral things, be determined by looking at N value, then Z effective. So let's remember that third criteria was, sizes relating to things that are charged ions. So the idea here is where you find electrons is what dictates the size. So to form a cation, how are electrons involved? What do you have to do to the electrons to make a cation? You take one out. So if there are less electrons on an atom, wouldn't you imagine that it gets smaller? Because there's literally just less electrons. But the true reason is because there's less electrons, there's less repulsion, all right, between electrons, so that's why it gets smaller, because there's less electrons repelling one another. So I guess the answer here, sodium is always larger than sodium plus. Okay, and then this idea continues if we continued taking off electrons. So size of your cation decreases as the positive charge increases. So iron 3+ is the smallest here, because literally there's the least amount of electrons, versus iron neutral has the most electrons. All right, so I think anions, cations, those ones are a little bit more straightforward. All right, less cations, you have to remove electrons, they become smaller. Just keep in the back of your mind, remember, electrons are negatively charged. Okay, then you can imagine if we just kind of, anticipate what's coming. We looked at cations, now anions. To form an anion, we have to add an electron. So we would predict that anion should be larger, right? Okay, but the true reason that anions are larger is because we're adding electrons. Remember, adding more electrons in a small space, we introduce repulsions. So then that's why the atom just swells up a little bit, gets a little bit bigger, because there's more electron-electron repulsions. So anions are always larger. So you can imagine which one of these particles is the largest, oxygen, O minus, or O2 minus. Which one's the largest? 2 minus, yes, because it has the most electrons. Okay, so there we go. Cations, anions. So now let's put them together in a special, special series, okay, where we can't figure out the size. Okay, we mentioned this before. What an isoelectronic series is, it's, or like what isoelectronic means. It just means that these two things share the same number of electrons. So if you look at these 5 different examples, the anions and the cations, if you check their electron configurations, all of them have the noble gas configuration of neon. They all have 10 electrons. But if we look at these elements, they all have 10 electrons, but how do they differ? How do they differ? Atomic number. Atomic number means number of protons. Yeah, so the number of protons do differ. So here's an isoelectronic series of a bunch of different ions, particles here. I mean, you already can see that O2 minus is the largest, but I want us to get there as well. All right, so we have 10 electrons on all of these, right, looking in to the nucleus. So the nucleus on oxygen, what's the charge of the nucleus on oxygen? How many protons does it have? 8. So those 10 electrons are looking into the nucleus and they see a +8. Versus fluorine, or a fluoride in this case, what is the charge of its nucleus? +9. So those 10 electrons are looking in on fluorine and seeing a +9. Sodium, it looks in, it sees a +11, magnesium a +12, and aluminum a +13. Now, do you kind of see where the sizes are coming into play here? All right, where it's the same 10 electrons looking at different charged nuclei. So do you see which particle is the smallest? It's the one that has the most attraction. So it's aluminum 3+ is actually the smallest, because those 10 electrons look in and see a +13, versus oxygen, 10 electrons are looking in and only see a measly +8. So those electrons are going to be on average further away, all right? Yeah, so O2 minus is gonna be largest, and aluminum is gonna be smallest. Really what we just calculated is the Z effective, or effective nuclear charge of these different particles. Z is changing for all of them, but the S, the shielding, is not changing for those. So really, we just kind of did like a lazy way of Z effective for these particles. All right. So are we going to do, okay, yes. So let's put it all together and pick the larger atom or ion of all of these pairs. All right. So, and the reason. Okay, so let's pick the larger one. So in general, if it's larger, that means that electron feels less attraction to the nucleus. So keep that in mind, all right? Okay, so I want us to state the reason as well. So I oftentimes look at the two elements, see how they differ, and see if I can't come up with a reason. So oxygen and carbon. How are they similar? How are they different? Do they share the same N? Can we distinguish them between N, the N value? No, because they're both N equals 2, right? So they're both the same energy level, yikes. So what do we refer to next? Z effective, yes. And so oxygen is +6, carbon is +4. So on which atom will the valence electron be less attracted to the nucleus, therefore be larger? Carbon, yes. And so the reason that we did here is because Z effective. N is the same, so we can't distinguish. So next we move on to Z effective. Good, all right. Next one, Arsenic and my favorite element, what is SB? Antimony. Doesn't matter, just locate it on the periodic table. So how do they differ? Different N's. So this one hopefully is straightforward. You see, okay, the N values are different. What is arsenic's N value? N equals 2, 3, 4. And then antimony is N equals 5. So which one's bigger? 5. Yeah, so antimony. So this, we came up with this conclusion because the N values are different. All right, what about potassium and calcium? Which one's bigger? Potassium. What reason? Z effective. Yeah, so we remember, so the kind of the thought process here is you look at the N first, you see that they're the same, they're both N equals 4, so I can't distinguish. So then the next step is to look at Z effective, and we see that potassium is +1, calcium is +2. If you're a moth that's attracted to positive things, like an electron, where are you more attracted to? A +2, so that one's smaller. So the +1 will be bigger. Okay, and so the reason, yeah, is the effective. All right, next one, nickel and nickel 2+, which one's bigger? The nickel 2+? No, okay, yes, it's the neutral nickel. Why? There's just more electrons there, so really it's because there's more repulsion, because there's more electrons in the non-cation version. Okay, F and F minus. F minus, again for the same reason, there's literally more electrons there. Okay, last one, K plus and K plus and Cl minus. This one's tricky. This one's tricky because you might look at these elements and be like, oh yeah, K plus is N equals 4, or sorry, K is N equals 4, Cl is N equals 3, so you might say K plus. But that's not right. What makes these two particles special? They're electrons. They're isoelectronic. They both have 18 electrons. Yes. So when they both have the same number of electrons, what do we look at? Number of protons in the nucleus. Essentially, we're calculating Z effective. So how many protons? So both of them have 18 electrons. Right? So this is kind of like the exception. It's the one that kind of doesn't fit. Potassium has how many protons that those electrons can look into? +19. Chlorine has +17. So those 18 electrons, think about, okay, what are they going to be more attracted to? They're going to be more attracted to the +19. And that will make a smaller ion. So we want the other one. We want the bigger one. So in this case, Cl minus is the larger one. And really the reasoning is because Z effective. They have different Z effectives. Okay, so that's probably the hardest one because you might accidentally look at just N values. Let me do one more because I saw one of these on a practice thing and I don't have an example of this. Okay, so let me, okay. Barium 2+ and chloride minus. Which one's bigger? Barium 2+ and chloride minus. It might help to think about how many electrons do each of them have, because we're talking about cations and anions, right? Okay. Does anyone have an answer they want to share they think it is? Which one's, what did I say? Which one's larger? Larger, larger. Barium 2+ or chloride minus? Barium is larger, yes. It is larger. The reason, okay? Well, look, barium 1 is a lot heavier. It's a lot heavier, but I'll prove it to you. The electron configuration for barium, it's a 2+ cation. So when you remove 2 electrons, what is its electron configuration? Krypton, yes. Krypton, which is N equals what? 5? 5, right? Versus chloride, we're taking chlorine, we're making a anion, so we're adding an electron. So what is its electron configuration? Argon, which is N equals what? 3? Is it 3? Yes, 3. So really, this question is about N value, all right? So we see that for barium 2+, it's N equals 5, so it's gonna be so much bigger, so much bigger. Good? Okay. So that's a little bit of a harder one. That's a little bit of a harder one. Again, electron configurations can help you. Don't try to overthink it. Okay, good? All right, let's keep going. All right, so those are the size trends. It's gonna come back to haunt us. Remember, N increases, electrons get further away as we go down a group. Effective nuclear charge increases as we go left to right. So size decreases. So those trends relate to ionization energy too. So ionization energy is the energy to remove an electron from an atom, from a gas phase atom. I should mention that. I forgot to add that here. It should be from an element, an atom, element in the gas phase. That's what you see here. So we can write a reaction to represent the energy. So that's the energy required to remove that electron. So we see that right here in these examples for sodium. So we have a neutral sodium gas atom floating around. We remove an electron from it. We form its cation. So we're separating a positive and negative charge. Think to yourself, does that require energy or does that release energy? Requires. Yeah, they're like plus and minus are attracted to one another and you're trying to rip them apart. So these ionization energies, they're always positive values that are in like kilojoules per mole. Always. Okay, because we're removing electrons from some type of, it's attracted to the nucleus. The idea of like electrons, when we remove them, in order to form calcium 2+, we don't just remove one electron, we remove 2 electrons. So we can successively remove electrons too. The idea here with ionization energy is that we remove electrons one at a time. So this next number here, the ionization energy, this next equation, is we take the product from the previous ionization and we make it the reactant in the next one, and we remove another electron. So we see here, this is us removing that second electron, so second ionization energy, forming a sodium 2+ cation. So this will also require energy. It's actually going to require a ton of energy, also kilojoules per mole. So that's the equation for ionization energy, energy to remove an electron. Now the trends that we talk about, really, you want to just think about how attracted is the electron to the nucleus. That relates to Z effective. And you want to think about how close the electron is to the nucleus. That is related to N. Both of those factors will change your ionization energy. Because the idea here, do I have the trends here? Yeah. So in general, what helps you here is that just smaller size means higher ionization energy. The smaller that atom is, because the idea if like I'm a dragon, like hoarding all of my electrons, they're all like right under me, okay? They're all really close to me. Is it gonna be easy or hard to take an electron from me? It's gonna be real hard, versus if I just let my electrons free roam, like my chickens, is it easy or hard to remove an electron if you just let them free roam? It's easy. And so it's the same idea, okay? So we just want to think about where is the electron and like how attracted it is. And that'll help you figure out how much energy it requires to rip it off. Ionization energy decreases going down a group because of the N value. Basically, N value increases, electrons are further away, easier to pluck off. Versus left to right, ionization energy increases because atoms get smaller, because Z effective gets higher as we go left to right. If you forget, all of these trends really relate to, what equation is this? Potential energy. So same idea, Q1, Q2, that's attractions, that's Z effective. So if you forget, that's Z effective. D, all right, that's distance your electron is from your nucleus. That is related to your N value. So again, all of this, basically we're just changing potential energy of our system. And so it all relates back to this equation and attractions. Okay, so a couple of exceptions. So we see, over here, the smallest atoms have high electron ionization energies. The largest atoms have really low ionization energies. There's a couple exceptions. Okay, what you see here is across our groups in this graph, it goes upwards, but there's a couple blips. So those blips are these exceptions. So the first one is between 2A and 3A elements, beryllium and boron. Pretend you're an electron plucker, right? An electron plucker to pluck off electrons. Which electron is easiest to pluck off? B, that one electron right there, because it's alone. Think about it like a chicken. It's just like a chicken that's, well, I know it's sad, but they're animals. Yeah, so that one chicken that's all the way over here is going to be easier than normal, all right? Just a tad bit more easy than these two that are all paired up buddy system together. So that one electron is just going to be slightly easier to remove because it's alone. Right, and that's what we see in this graph. If we go over here to the graph, you see, I think beryllium is here, and then boron is just slightly lower, but then the trend continues. Okay, same idea. Exception between 5A and 6A elements. So if you are an electron plucker, which electron is easiest to remove? The one on which atom? Think of them as chickens. The one on, no, not the one on nitrogen. It's actually the one on oxygen. It's the one that's spinning the wrong way. It's the weird one. So unfortunately, the weird one is easiest to pluck off. Did anyone think that? Okay, no. Because we don't have predators in this room. That's why. Everyone's real good people. Yeah, so it's the electron that's spinning the other way is the weird one and is easiest to pluck off. Yes, and so that's what we see in this little blip over here, nitrogen and oxygen, but we see that it continues off. And you see it's just like a tiny energy difference. Remember in chapter 6, we talked about we get extra energy stability when we have half-filled subshells, all right? So those are extra stable. And so again, taking one of those off here, all right, will be easier because we get this really, really stable configuration. All right, did no one thought the one there? You got this one real easy, but it's for the same reason. It's like the weird one out. Okay, so that is ionization energy. So mentioning removing electrons, okay, we have to be able to form, not just +1 cations, we need to be able to form, +2, +3, so we have to take off multiple electrons, but the idea is we have to take off those electrons one at a time, and each of those electrons, when they come off, have their own energies. So that's what this table is, a successive ionization energy chart. It shows you the energies to remove electrons one at a time. So the idea here, let's look at sodium. Okay, sodium, that first electron only takes about 500 kilojoules of energy to remove. But what about the second electron? Well, do you think that is energetically favorable to remove that second electron off of sodium? No, that's a really big number. But let's think of it. Taking off that second electron on sodium would make a sodium 2+. Is that something you've ever run across in your life? No. So this chart is showing you energetically why sodium forms a +1 cation, because there's one valence electron, right? One valence electron. And so if we removed an additional electron, we're literally removing inner core electrons. All right, so that big jump shows, hey, it's not energetically favorable to go into that inner core. So same idea here. You can see magnesium has 2 low numbers and then a huge jump. So based upon this, magnesium, don't look at the periodic table, magnesium will form what charge cation? 2+. Now look at the periodic table. Does that match what we know? Yes, it does. What about aluminum? We see 3 numbers, 3 somewhat low numbers, and then a huge jump. And so that means aluminum is most likely to lose 3 electrons. And so to note here, note how even if aluminum loses 3 electrons, see how it slowly goes up. Each one, it goes up and up and up. And that's because aluminum is gaining charge within there. So this is why valence electrons, why we care about valence electrons. They are the electrons that are easiest to remove. So you guys are packing up, but let's look at this graph for successive ionization energies. Just look at it. How many valence electrons does it have? 6? 6? How do we read this graph? The first 4 numbers are really low, small amount of energy to remove electrons. Doesn't that describe a valence electron? Are the 5th and 6th electron valence electrons? No, there's a huge jump. It costs way too much energy money to rip off those electrons. So 4 valence electrons, if I tell you it's n equals 2, what element is it? Carbon. Yes, it's carbon. That's it. Yes, okay. All right. I'll see you on Wednesday.